Hi everybody. We are going to estimate population means by creating a confidence interval. Okay, so basically these notes are going to follow the exact same format as what we did with proportions, except we're going to use means instead of proportions. So our scenario is we want to estimate the true average daily screen time for a typical South River student. So we have a simple random sample of 30 student screen times from a single day, and their sample mean was 6.4 hours with a standard deviation of 1.08 hours. So this sample mean, X bar, is our unbiased estimator of mu. Okay, so because it's unbiased, we would estimate that mu is pretty close to X bar. Okay, but if I took a different sample of 30 students, I'm probably going to get a different X bar, so I have to take into consideration how much variation there is in that sampling distribution. Okay, so based on one sample, it's not correct to conclude that the screen time is 6.4 hours on average. Instead, we're going to take that X bar and use it to estimate the mean by making a confidence interval and getting a range. Okay, so if our data is from a simple random sample and it's sufficiently large in our sample size, then we know our sampling distribution has a mean of mu and a standard deviation of sigma over the square root of n, okay? But we have a problem. We don't know sigma, okay, because we don't know anything about the population parameters, okay? So we can't use that in that formula. So instead, we're going to estimate sigma so we can use our inference methods. To do that, we're going to use the standard deviation from our sample. Okay, so the spread from our 30 students. We were going to use the 1.08 hours. So with that as our estimate, now the standard error of our sample mean is going to be that sample standard deviation divided by the square root of n. Okay, so same formula, just using a different standard deviation. Okay, now back in chapter 7, we used that z-score formula, okay, to figure out how many standard deviations we were away from the mean. Okay, but now that I'm not using sigma and I'm using my sample mean, okay, I'm going to have a different kind of spread, okay? So now my distribution is going to have more spread, okay, and not follow the normal distribution. And if I don't follow the normal distribution, I can't call it a z-score, which means I can't use z-scores and I can't use z-star, okay? So your sample means are going to follow a new distribution called the t distribution. So instead of a z-star, we're going to use a t-star, okay? And just like z, it tells us how many standardized units X bar is from the mean. Now, in order to describe a t distribution, we have to identify the degrees of freedom because there's a different t statistic for every sample size. So our degrees of freedom for the one sample t statistic is going to be our sample size minus 1. This distribution is symmetric about 0, is bell-shaped, but it's got more spread, okay, which means there's more variation. As the degrees of freedom increase, though, it's going to get closer and closer to the normal distribution because our sample size is getting bigger and bigger, okay, and t is getting closer and closer to z. Okay, so to make the actual confidence interval, it's going to follow the same format that you're going to get on your AP formula packet. Statistic plus or minus the critical value times the standard error, okay? But now the statistic instead of p hat is our X bar, critical value is t star instead of z star, and your standard error is the formula we use for means with the sample standard deviation, okay? Remember, your critical value times your standard error is your margin of error, okay, which you add or subtract to get your interval, okay? And we'll work more with that next week. Right, so in the t table, if you look at that table in your AP formula packet or in your textbook, it uses the area to the right of t, okay? Just a fact to remember about that. T procedures are only correct to use when your population is normal. Okay, so we have to be able to assume that our population is normal, okay, to be able to use our t procedures. They're strongly influenced by outliers. So if we have outliers and the sample size is small, then we can't have reliable results and our confidence interval is not going to mean anything to us. okay? So in order to make sure we don't have outliers, you have to check your data, okay? How do you do that? You either do a sketch of the box plot of your sample data or histogram, and all it has to be is a rough sketch. Your calculator can do that for you, okay? Because they're going to give you the data. Okay, so when to use the T procedure. So what to check in your assumptions and conditions to make sure you can continue with the do part of your state plan do conclude, okay? So if your sample size is less than 15, do not use T if the data is severely skewed. If it's at least 15, but less than 30, only use T procedures if the data is unimodal and reasonably symmetric. If your sample size is at least 30, you can use T even if your data is skewed. So 30 is that magic number again. If your sample size is bigger than that, you're good to go. You don't have to check your data or anything like that. All right, now special case, if your sample size is greater than 30, you will not be marked wrong if you use Z-star as your critical value, because your sample size is getting so big that you can use normal calculations. If you stick with T for means all the time, that's fine too. Okay, so let's talk about some of the big ideas. So your conditions when you're doing your plan and your state plan do conclude. We need to make sure that we have a random sample, okay? Assume if it's not, and we want our sample size to be less than or equal to 10% of the population size. We need to check our normal conditions. So either we're told in the problem that the population distribution is normal, our sample size is big enough, or we checked the sample data and it was symmetric and had no outliers, okay? If you meet one of those things, then you're okay to check the normal condition and proceed with T. The critical values, okay, so T star is the critical value we use for means. Remember, your degrees of freedom is n-1. If you use the table, and this is the same table we were using last class, and your degrees of freedom is not in that left-hand column, just round down to the next one. Always round down, not up. All right, in your calculator, we used NV norm to get Z stars, okay? Right under NV norm is NVT. What you're going to type in is the left area, so your confidence level, and the tail area, comma, and your degrees of freedom. Okay, so for example, say we wanted to construct a 95% confidence interval, and our sample size was 16. Okay, so our degrees of freedom is 15. If you check, your left area is going to be 95 plus that tail of 2.5%. So in NVT, I type in 0.975, my degrees of freedom, and my T star is going to turn out to be 2.131. If you go in your table and you line up the degrees of freedom row with the 95% confidence column, that T star will match. Okay, you can use either method you like. Okay, and I can show you in the calculator. NVT, right under NV norm, okay? Type in your area, your degrees of freedom, and there's your T star, okay?